as I do in most classes, I put up a little bit of a review on the blackboard so that I can connect what we're doing today to what we did in past classes. So I find that that's a good, it's a good way to sort of bring you back to where we were at the end of the previous class. I put this up. We'll get to it later. This is just an example that I'm going to refer to later, which was with one CSTR or two CSTRs in the series, what C8 prime tilde was. I'm not using that now, but that's an example I'll refer to later, so I want to remind you what those results were. If you remember, the issue we had that we were looking at in the last hour was that when you do use Laplace transforms, which hopefully you're already convinced that that's a really nice way to solve these problems, you take your governing equations, you Laplace transform them. So you go from the time domain to the S domain, and that seems like almost magically all the derivatives and the integrals disappear and they become algebraic equations. Then you solve the algebraic equations and you get an answer in terms of S that you want to then transform back to the time domain, because the time domain is where we live. We don't live in the S domain. Might be an interesting way to live in the S domain, but we live in the time domain. So that's what we're interested in. And of course we have this table, which the table we have is restricted. It only has 18 entries. If you go to better books, they may have 5 pages, tables that are 5 pages long. But you're not going to have all possible functions there. And many times, the answer you get can be broken up into a sum of terms, each one of which is in the table. So the question is, how do you break up a big equation into a sum of smaller equations, each one of which hopefully you can find in the table. So that was and that's called partial fractions. So we started doing that last time. We actually, the previous class, before last time, I know that was a long time ago, we did at the very end, we did one example, a simple one. And then we started doing it more generally in the last class. So in the last class we said, let's say the thing we want to invert is a ratio of a numerator and a denominator d. That's why I chose n tilde and d tilde. And the assumption is, in this class, that to make life easy, we're assuming that both n tilde and d tilde are polynomials. And we're assuming they have no common factors. We've already canceled out the common factors. So here, presumably, we can factor d tilde into in this form, where again, if the leading coefficient was anything other than 1, I stick it in the numerator, so the denominator just looks like this. And we said there are three cases we would look at. One where all of the roots, the S1 through Sn, are all different. And we saw that in that case, we could write n tilde over d tilde as a sum of a constant over S minus S1 plus a constant over S minus S2, etc. And when I take a Laplace transform of 1 over S minus S1, I just get e to the S1t. So that was from the table. On the other hand, if, let's say, n, where n is something greater than 1, n is greater than 1, of the factors are the same, so then I have S minus S1 to the n, where n is greater than 1, times the rest of them. Then things get a little different, and what we saw is that n tilde, if we could write d tilde this way, that only one of the roots is a multiple root, and the others are simple roots, then we could write n tilde over d tilde. That's why I shouldn't take pictures until I fix the mistakes. Is equal to c1 over s minus s1 plus c2 over s minus s1 squared, c n plus 1 over s minus s1 to the n plus 1, plus, again, the remainder, where we came up with expressions for the CIs in terms of various derivatives of this evaluated at S1. I didn't bother rewriting those. Again, I had an expression also for the MIs here, the CI is MI and SI, and MI tilde SI. And so we had this. And then the third example we were doing was a case where what we said is that even though time is a real variable, and generally time is always non-negative, or is generally not negative, S, when we go to the S domain, S can be the complex number. So, and what we said though, is since the coefficients in our equation are all real, generally, because they come from real physical things, then if I have a polynomial where the coefficients of the polynomial are all real, if any of the roots of the polynomial are complex, then we get a complex number and its complex conjugate. You can see that, for example, in the quadratic formula. If you have ax squared plus bx plus c, sometimes the x's can be complex, but it's always with a complex conjugate. Remember, it's minus b plus or minus the square root. So the minus b is real, and that square root might be, if the thing inside the square root is negative, then I get an imaginary part there, but it's always with the plus or minus. Minus b plus the square root is the complex conjugate of minus b minus the square root. So for quadratic, you have the complete solution. You can see that. It's obvious that when you have one, you have its complex conjugate. And it's not that difficult to prove that for an arbitrary polynomial. If all the coefficients are real, then whenever you have a root that's complex, you also have to have its complex conjugate, so that when you multiply all these things out, all the coefficients turn out to be real. If you didn't have a complex conjugate, then you would have some i's sticking out in the coefficients. So we said, okay, we're going to analyze this. And again, we're just looking at a situation where only one of the roots is complex. Only two of the roots are complex and they're complex conjugates. Obviously, I can have multiple of those, but the extension is sort of straightforward. And we noted at the end of the last hour that if I write them as alpha plus I omega and alpha minus I omega, when I combine them into one, when I multiply S minus alpha plus I omega and S minus alpha minus I omega, I get S minus alpha squared plus omega squared in the denominator. And when so I write n tilde over d tilde is this ratio plus whatever else is left. And this has all the other roots of, all the other factors in d tilde. And we noted, using what we learned from case A, that we can write this as some m, the part of m, the part of m that doesn't have one of these, one of the factors in it. M tilde of alpha minus I omega over S minus alpha minus I omega plus M1 tilde of alpha plus I omega divided by S minus alpha plus I omega plus a remainder. And what we're going to do now, in the beginning of the class, is we're going to find the relationship between M1 tilde and M2 tilde. And then what we're going to do is then do the inversion of this and show that we're going to get sines and cosines. That's sort of the coming attractions. And in order to do that, we noted that sine is either, sine, for example, of omega t is e to the I omega t minus e to the minus I omega t to 2i. The cosine is e to the I omega t plus e to the minus I omega t over 2. And a little things about complex numbers. If we take the sum of two complex numbers, of the sum of the complex conjugates of two numbers, we get the complex conjugate of the sum. And similarly for the product. And if the sums and the products work that way, a polynomial is just a bunch of sums and products. So the polynomial of the complex conjugate of z is just the complex conjugate of the polynomial of z. And one more thing I need to show before I go on is because m tilde, remember we said that n tilde and d tilde are presumed to be polynomials. So it says m tilde has n tilde in it, it's a polynomial, but it also can have the other factors in d tilde in the denominator in it as well. So m tilde can be a ratio of polynomials. So what I need to also show is that z1 over z2 complex conjugate is equal to z1 complex conjugate over z2 complex conjugate. And there's a little bit of algebra here. It's not hard, but it's algebra we're going to use later in the semester, so it's worth doing that. So let's just go through that and show this last thing. So let's calculate Z1 over Z2. So I'm going to write this is going to be x1 plus iy1 over x2 plus iy2. Now, how do I figure out what the real and the imaginary part of this is if I've got an I in the denominator as well as in the numerator? Well, the way I do that is I need to get rid of the I in the denominator so that the denominator is real, and that way I can just read the numerator divided by the denominator and see what's imaginary and what's real. The way I do that is I multiply by the complex conjugate. So I multiply by 1, but this 1 is the complex conjugate of the denominator. And when I do that, then the denominator just becomes x2 squared minus I squared y2 squared. Minus I squared is plus 1. Divided, and plus I times something. Well, plus I times x2 y2 minus I times x2 y2. So they cancel out, so now the denominator is real. And now I look at the numerator. So I get x1, x2, and then I multiply these two together. Minus I squared is a plus y1, y2. And then I take plus I x2, y1 minus I times x1, y2. So now if I took the complex conjugate of this, I would just flip the I to minus I. Well, let's look at Z1 bar over Z2 bar. It's the same algebra. Except this now is x1 minus iy1 over x2 minus iy2. And now to make this, the denominator, real, I have to multiply it by its complex conjugate, which is x2 plus iy2. And again, the denominator is going to be x2 squared plus y2 squared. But the numerator now is going to be x1, x2 plus y1, y2 plus I times x1, y2 minus I times x2, y1. And now I want to compare these two expressions. This is Z1 over Z2. This is Z1 bar over Z2 bar. It's the same denominator. It's the same real part in the numerator. The difference is, here I've got a plus x2y1. Here I have a minus x2y1. Here I have a minus x1y2. Here I have a plus x1y2. So clearly, flipping I to minus I will change one to the other. So that says the complex conjugate of this will be equal to this, which is exactly what I was trying to prove. Questions? Okay, so that's telling me that now I know a lot about M2 and M1. I know that even though they're ratios, they may be ratios of polynomials, if I take the complex conjugate of, if I take M2 tilde, if I take the complex conjugate of this, I'm going to just get M2 tilde of that alpha plus I omega. Okay, so now let's know that M tilde from here of S minus, so now I'm just going to think of this thing as Z and this thing as Z bar to save myself a little bit of writing. So M tilde of S over S minus Z, S minus Z bar. So that's what this is. That's equal to M2 tilde of Z bar over S minus Z bar plus M1 tilde of Z over S minus Z. So I just rewrote that this was equal to the sum of these two. But instead of writing alpha plus I omega, I called that Z, and Z bar is alpha minus I omega. And now I would like to find, I'm going to do some algebra, trying to find a relationship between M1 tilde and M2 tilde. So let's multiply both sides by S minus Z bar. So it says m tilde of s is equal to m2 tilde of z bar. When I multiply by s minus z bars, those cancel, and I just get an s minus z here. And then I have plus m1 tilde of z. And when I multiply by s minus z, that cancels, and I'm just left with s minus z bar. And now let's evaluate this both at z and at z bar. So m tilde of z, well, if I'm at z, this just becomes z minus z. That term drops out. I just get m1 tilde of z times z minus z bar. Well, what is z minus z bar? Z is this, z bar is that. So this minus this, alpha goes out, and I get I omega minus minus I omega. I get 2I omega. And how about m tilde of z bar? Well, at m tilde of z bar, this term is 0. So I just get m2 tilde of z bar times z bar minus z. What's z bar minus z? It's this minus this. Alpha minus alpha is 0, minus I omega is minus 2I omega. And we know from what I just proved over here that if I take that this is just the bar of this, because m tilde of z bar is just m bar of z tilde of z. So I know that from here, we know that m tilde of z bar is just equal to m tilde bar of z. In other words, m2 tilde of z bar minus 2I omega is equal to the bar of this. The bar of this is m1 tilde of z bar times minus 2I omega. Because when I take the bar of the product, I take the product of the bars. And the product of the bar of this is just minus 2I omega. So immediately this cancels. And what I'm left with is, and let's see what this is. This thing now is m1 tilde of z bar, because I can take the bar inside. So I have m2 tilde of z bar is equal to m1 tilde of z bar. So m1 and m2 are the same function. So therefore, m1 tilde of z is equal to m2 tilde of z. So m1 and m2 are the same function. In which case, m tilde of s over s minus z, well, I can just s minus alpha squared plus omega squared. That's equal to, so since they're the same, I can just give them one name. I have m1 tilde of z bar, m1 tilde of alpha minus I omega over s minus alpha minus I omega plus m1 tilde of alpha plus I omega over s minus alpha plus I omega. So now I'm not bothering with the remainder, I'm just looking at the first term. And this is going to be some complex number. When I evaluate it, it's some ratio of polynomials. It's some ratio of polynomials at this argument. So that's just going to be some complex number, whatever it is. And notice, so this is some complex number, which I can call a minus ib. It has a real part and an imaginary part. I'll call the real part a and the imaginary part b. Since this is the same function, but evaluated at the complex conjugate, it's the complex conjugate of this thing. So then this thing is just equal to, if this is a minus ib, this is just a plus ib. factor. I know there's a lot of algebraic manipulation here, but what I could do is, like the book, just tell you the answer, and then you won't believe me. So I go through the details. If you don't like the details, you can just remember the answer. But this way, if you're a little more curious, I've shown it to you. This is not higher mathematics, it's just lots of algebra. Okay, so if you remember, when you invert 1 over s minus s1, you get e to the s1t. So we know that the loss transform inverse of m tilde s, of s minus alpha squared plus omega squared, is now going to be equal to a plus ib times the, this should have been a minus, times e to that power, times e to the st. So e to the alpha minus I omega t plus a minus ib times e to the alpha plus I omega times t. So how did I go from here to here? This is a coefficient, and I have s minus something, and 1 over s minus something just inverts to give me e to the that something times t. E to t times that something. And here's e to the t times that something. If you miss a step, you should stop me. If you're not understanding a step in the algebra, stop me and I'll go over it again. Okay, so let's factor this out. Let's notice that all the terms have an e to the alpha t. So let's factor out an e to the alpha on the outside. And now I can notice that I have a times e to the I omega t. That's this term, like that. And then I have a times e to the minus I omega t. And then I have a plus, and then I have a plus ib. Plus ib times, well, this is a minus plus ib, minus ib here, times e to the I omega t. And then here I have a plus, I should do it the other way around, plus ib times e to the minus I omega t, minus e to the plus I omega t. And you wipe that and do this. And, oh no, that's okay. So there we're fine. So all I did is I factored, I took the 2 terms for the A and put them here, and the 2 terms for the B and I put them there. Now I'm going to multiply and divide by 2. That was easy. And then I'm also going to multiply and divide by 2i over here. So that color's too close. So now I'm going to divide by 2 and multiply by 2. But now I'm also going to multiply and divide by I. So I have an I, and now I have an I here. I squared is minus 1. So this guy will change this to a plus and this to a minus. And notice what I have here. This is equal to e to the alpha t times, I'm going to factor out 2, a times, well, this is nothing more than cosine. Cosine omega t. And this, I factored out 2, is nothing more than the sine of omega. So what we find is when we have 2 roots, 2 zeros of d tilde, 2 roots of n tilde over d tilde, that are complex conjugates of each other. First, we have a simple relationship between the coefficients. And when we put them all together and we do the inverse, we get sines and cosines. So we get something that oscillates. It oscillates, but it's also multiplied by the e to the alpha t. Any questions on that so far, before we draw some physical meaning from all this? Questions? Okay, so let's put it all together, and let's see what they mean. So let's take cases A and B and C, and put them together. And that tells me that L dot Gauss transform inverse of any tilde over E tilde is going to be a sum of terms for the ones where the roots are distinct. So I've got a CI e to the SI. I got a bunch of terms that look like that. And now, so this is the case A part. I've got a bunch of terms that just look like that. And now I have another bunch of terms. The case B part, where I've got, what I want to give these letters for the names of my names. I think I call them C's. No, I call these A's. I'm going to leave them as C's. I don't care. So let's call these, I don't know, DI's. And I should have double something. Yeah. Okay, so what did I do here? So here, for each of the i's, these correspond to the SI's, where the SI's are simple roots, they're not multiple roots, and they're all different, and they're all real. Here, for each multiple root, so each one of these, each root that's a multiple root, I have a bunch of terms with all the various powers of t times e to the sjt. And I might have more than one that has multiple roots. So for each one, I have this sum, and I may have multiple ones that look like this, that are multiple roots. So this is all B. And then I have C, which is a sum of 2e to the alpha t, A, K, cosine omega t, plus bk, sine omega t. And these are alpha k and omega k. And here I'm summing over all of the pairs of complex conjugates. So the k's go over all of the SI's that are pairs of complex conjugates. There might be more than one. Now, one thing I didn't go through is D, which is, let's say I have pairs of complex conjugates that are multiple roots. So instead of this being S minus alpha minus omega, it's S minus alpha minus omega quantity squared, or cubed. In which case, I will get a combination of these, which I didn't go through, but I'll have a sum on J, actually I should L, sum on L, DL, D1L plus D2L, T plus dot dot dot, times 2e to the alpha LT times AL cosine omega FT plus BL sine omega. So here I have just exponentials. Here I have exponentials times power of t. Here I've got exponential times sine and cosine. And here I can have exponential times sine and cosine times powers of t. All those are possible. And what we've done here is we've come up with the most general solution you can think of for the most general case where n tilde and d tilde are polynomials. Actually, all we really needed was d tilde being a polynomial. As long as d tilde is a polynomial, I can only have real and complex roots. There's nothing else. That's another thing that you would prove in an analysis class, that if you have a polynomial of any order with real coefficients, or even complex coefficients, all the solutions are within the complex numbers. And that you have enough of them. And there are either simple roots or multiple roots. We've looked at all possibilities. So the simple real roots, the multiple real roots, the simple complex roots, the multiple complex roots. We've got them all. So we know what the general solution looks like. And notice that all of them, every term here, has e to the, these roots are real, so it has e to the real part, s is real already, t, e to the st. E to the real part, alpha t, e to the real part, alpha t. Now, in this case, it's multiplied by powers of t. In this case, it's multiplied by sine and cosine. And here it's multiplied by the powers of t and sine and cosine. But the exponential always wins. So what does that tell me? Before we get too lost in the mathematics, let's remember, what did we do? We're looking at a physical problem in the time domain. We have a differential equation, for example, a CSTR equation, or some other, or 20 CSTRs in series. We have various derivatives of the variable of interest, say the outlet concentration, with respect to time. We transform into the S domain. We do our manipulations. We want to go back to the time domain. Going back to the time domain is we want to know what the outlet is as a function of time. So we want to know, we did some sort of perturbation. For example, in the CSTR, we changed CA in. We changed the inlet volumetric flow rate. We changed some things. We want to know what's going to happen to the outlet. Will the outlet settle down to a new steady state? Or will the outlet blow up or do something crazy? Well, now we can see what it's going to do. If we happen to have complex conjugate solutions, you can have a situation where the outlet, even though the input, for example, CA in versus T, even though the input change was a step, the output oscillates. It's got sines and cosines. Isn't that weird? I did a constant to a constant, and the output oscillates. It's possible. But it doesn't just oscillate. If alpha L is positive, it can oscillate and grow. That's really bad. Let's say that were the pressure instead of the concentration. If it were the pressure, the reactor could blow up. If alpha is negative, then it's okay. It oscillates a little bit, but the oscillation dies down and eventually goes to a steady state. Here's alpha positive, alpha negative. And in fact, we should look at this alpha positive or alpha negative, and we can draw some conclusions. When the system blows up, we're going to call that unstable. So the system is stable if all of the SIs have negative real parts. So if all of these SIs, there's J, alpha, alpha, if these are real already, if they're negative, we're okay. And if these are negative, then even though they have some oscillations, they all die down and it's stable. That's great. That's what we want. We want it to be stable. So that would be great. We want it to be stable. What happens when is it unstable? System is unstable, meaning it can blow up, if even one alpha of the SIs has a positive real part. All you need, even though I have all these terms, all you need is one of them to have a positive exponential, and you're screwed. So it's kind of unfair. I can have 100 roots. If 99 of them are good, but one of them's bad, it's still unstable. So now what happens, then there are some intermediate cases. What if one of the roots is 0? Has 0 real part. Well, it depends which one. If this one has a 0 real part, then that just says that the new value goes to a constant, which is different from the old value. Because if we're dealing with deviation variables, the deviation variable goes to a constant rather than to 0. Well, that's what typically happens in CSTR if I have a step change in the input. Then the output eventually goes to a new constant value. So that's okay, that's still stable. How about if it's one of these? If I have one of these and one of the S's has a 0 real part, it still grows. It grows as at least t to the first power. So as t goes on, it gets bigger and bigger and bigger, and it's unstable. So in case A, it's stable. Case B, it's unstable. Because it's unstable, it doesn't blow up exponentially, but it blows up linearly or quadratically. So it's not as bad. In other words, the reactor doesn't blow up right away, it may blow up next week. Still not very good. On the other hand, it does mean you have a little more time to react. How about case C? Case C, if one of the alphas has a 0 real part, then it's just going to oscillate with constant amplitude. So stable means it doesn't blow up. Unstable means it blows up. It's stable, but it oscillates. That may or may not be a good thing. So for example, the boiler in your basement of your building, the one that hasn't come on yet because it's still cold. If that boiler, if the temperature in that boiler oscillates too much, which happens, it oscillates because when people take showers in the morning, it uses up the hot water and then it fills up with cold water and it gets heated up again. Now, if the boiler's too small, then it runs out of hot water pretty often and has to get filled with cold water, so it oscillates more often. And the material of the boiler, the metal, doesn't like those oscillations, and eventually it breaks. So it breaks more quickly. So sometimes oscillations could be bad. There was a person named, a professor, died a long time ago, named Fritz Horn, who investigated certain chemical reactors that when they oscillate, in certain cases, you may get a higher overall conversion than if it operates at steady state. There are some unusual cases like that that he found. So sometimes an oscillation is not bad as long as it doesn't grow. Sometimes it's bad, sometimes it's not. How about for case D? Case D, if one of these has a 0 real part, yeah, I oscillate, but again, I'm multiplying by powers of t. So case D is like case B. It's unstable, Because even though I have the oscillation that doesn't grow exponentially, it does grow linearly. So that's also unstable. Are there any questions on the notion of stability? Now this is something that's very important for us to be able to analyze, the notion of stability. There can't be anything more important. Remember, the first goal of the control engineer is safety. So one of the most important thing that we can evaluate is the safety of something. And that is very much tied to the notion of whether it's stable or not. So it's really important to do that. And the nice thing about doing this with Laplace transforms is I don't need to actually carry out the inversion to know if it's stable. All I have to do is look at what I found, look at the denominator, and look at its factors. And I can just ask, does any of them have a positive real part? If any of them has a positive real part, it's unstable. If they all have negative real parts, it's stable. Before I even do the inversion, I can read it directly off from here, once I've factored that denominator. And of course, the case where I have some roots with 0 real part, again, I can do this test directly at this point. I don't need the rest of the blackboard to do that. I can do it right here. Questions? Any questions? You followed all the algebra? It's true. I mean, the algebra wasn't hard, but when you see it in front of you going by 90 miles an hour, it looks harder than it is. But you'll have pictures of this. The people who took pictures before the class started, remember you want to take the picture again because I had fixed some errors when I wrote it out. Okay, questions? All right, well, when I look at, say, CSTR, actually, let's do a simple example. Let's look at this particular case, the 2 CSTRs in series. If I look at 2 CSTRs in series, I have CA2 tilde prime. And that we said is equal to CA in prime tilde KP over 1 plus. So I've got KP over 1 plus ST1, 1 plus ST2. And let's look at a case where I did a step function. So if I did a step function CA in prime, remember that the Laplace transform of the step function was 1 over s, was the difference of 1 over s. So it's CA in prime, CA in prime over s, where this thing is equal to CA in prime tilde. See, it's good to be tall. I can reach the top of the blackboard. Professor Steiner can't reach the top of the blackboard. When she comes in here, she asks me to raise the top of the blackboard. I'm sure she has other advantages, but okay. So let's notice that this is in the form of n tilde over d tilde. It's in this form. N tilde happens to be a constant. It's kp over ca in prime. And by the way, here is the expression for kp, and here's the expression for the ti. Then there should be an kp2. I think you can imagine that if I had 5 CSTRs in series, I'd just have 5 factors like this. The denominator, d tilde, so n tilde, is just kp2 ca in prime. Well, just a constant. All right, it's all right. That's an example of a polynomial. How about d tilde? D tilde of s is s 1 plus st1, 1 plus st2. Why does the phone always ring during class? Actually, let's put it on airplane mode. Then it can't ring. Airplane mode. We're not on an airplane, but we'll pretend. Okay, so I want to write this in this form. So this is equal to, let's factor out a t1, a t2. And this is s minus 0, and this is s minus a minus 1 over t, 1. And this is s minus a minus 1 over t, 2. Because this would be s plus 1 over t minus t is 1 plus s2. So here, this is s1, this is s2, and this is s3. So let's write them out. S1 is 0, S2 is minus 1 over T1, S3 is minus 1 over T2. First thing is none of them are positive. So I'm not quite in this case because one of them is 0. So I'm in case C. So case C, well this case, I'm in here, where all of them are negative. These are both real and negative, so there are no case C's or D's because they're all real. There are actually no case B's. This is all case A. This is all case A. They're all real and there are no multiple roots. They're all real and no multiple roots. 2 of them are negative and 1 of them is 0. We said if they're all in case A and 1 of them is 0, that's okay. It's stable. And because I have 1, 0, that says that even though the input, CA in versus D, went from one constant to another, the output, CA T, also went from one constant to another. That is, I have a difference here. CA prime, CA2 prime. CA2 prime is a constant. It goes to a constant, it doesn't go to 0, because I have the 0 here. And the 0 means I have a constant. Now, if you remember, if instead of having a step function, just remember, the Laplace transform of theta of t is 1 over s. The Laplace transform of delta t is just 1. If I had a pulse at 0 instead of a step function, if I had a pulse instead of a step, then I wouldn't have had the 1 over s. Then this factor wouldn't be there. And then I would only have my two roots, both of which are real and negative. In which case, CA2 prime of t would just go back to 0, because I have e to the minus t1t, e to the minus t over little t over big T1, and e to the minus little t over big T2. So CA2 might go away, but eventually it would go back to the same value. Because all the roots would be real and negative. In this case, with the step function, all the roots are real, but there's one, all of them are negative except for 1, and 1 of them is 0. Is that example clear? So that hopefully makes what we've done here, brings it back down to earth. Brings it from math land to chemical engineering land.
Why for the pulse the first one goes to 0?
Can you say it a little louder, please?
Yeah, for the pulse you said the first one goes to 0? Or
The output goes to 0. Why is that? In the case of a pulse, I don't have this 1 over s in the denominator. If I don't have the 1 over s, that means I don't have this factor. I don't have an s1. So that says the solution for CA2 prime of t, not CA2 prime of tilde. When I go back to the t, that goes, I look here. And I only have these terms, because there are no multiple roots and no complex roots. They all look like this. If all the SIs are real and negative, every term has a negative exponential. All these terms, as t goes to infinity, go to 0. So I just have CA2 prime of t just to 0. Goes to 0. It goes there exponentially, but eventually makes it back to 0. Where this thing is not one exponential, it's often sum, it's the sum of 2 exponentials. Sum of 2 terms. So in this case, blue, CA CA2 prime of T is equal to coefficient C1 e to the minus T over T1 plus C2 e to the minus T over T2, where T1 and T2 are the two time constants. And if T1 and T2 happen to be the same, then it would just be a single exponential. But I have to be careful, because if T1 and T2, and maybe we should look at that case. Let's look at the case where T1 and T2 are different. This is the case where T1 and T2 are different. What if T1 and T2 are the same? If T1 equals to T2, then I'm no longer in case A, I'm in case B. I have multiple roots. So in that case, CA2 prime tilde is equal to KP2 CA in prime divided by S1 plus K, 1 plus S T1 squared. And let's look at the case where I have a step and a pulse. So I'm glad you brought up this question because I had forgotten to actually go through this example. So a lot of times when you ask a question, you remind me to do something I wanted to do and forgot to do. So that was okay, so let's look at this case. In this case, by exactly the same reasoning for a step change, then I have S1 is 0, but S2 equals S3 is equal to minus 1 over 2. So that says I'm in case B. And that says that what about what's going to happen here? Remember, let's just remind ourselves. If I have a power n plus 1, so here n is equal to 1 here because the power is 2, then I go to a maximum of S1, I have, let's see, so yeah. So that says the highest power here is going to be squared, so that means I'm going to get a t to the first. So that says I'm going to have from here, I'll have a d1 e to the minus t over t1 plus a d2 times t times e to the minus t over t1. We knew that already because we did it explicitly before we did Laplace transforms. But we notice that we get t e to the minus t over t1. So again, the exponential wins. The exponential wins because I'm in the case that even though one of the roots is 0, I'm in case, say I'm in case, slowly, yeah. One of the roots is 0. This root is 0. So let's look at that. The S2 and S3 give me these two terms, and this just gives me a C1, a C1. So let's just review. I've got a root that's 0, but that's a case A root. A case A root is 0, so I just get a C1 times e to the 0. The multiple root is not 0. So the multiple root is this, but its coefficient is not 0. Its real part is not 0. So I get d1 plus d2t times e to the s2t, which is e to the minus t over t1. So this is stable because the 0 root was not a multiple root. The 0 root was a case A root. The case A roots are allowed to be 0. Case A roots are allowed to be 0. The case B root is negative. That's okay. If the case B roots are negative, the exponential always wins over the powers of t. Is that clear? For the step. Is that clear? Yes? No? Maybe? Now let's look at the pulse in CA in prime. CA in prime. If I have a pulse, I no longer have this root at all. I just get d1 e to the t minus t over t1 plus d2 t e to the minus t over t1. There's no zero root. There's no zero, yes?
For the pulses, why do we get rid of the S?
Because where did the S name come from? The S came from the Laplace transform of the input. So the input had to change, which was, if it's a step function, then we get the 1 over S comes from the fact that it's a step function, the input. That's right. But if the input is a pulse, not a step, instead of it being 1 over S, it's just 1. So I don't have the 1 over S. Good that you asked that, because not everyone might have followed. So again, both of these situations are stable. Other questions? So again, when we talk about having zero roots, those except obviously if all the real parts are negative, no problem. It doesn't matter if I'm case A, B, C, or D. If there's one with a positive real part, it doesn't matter whether it's case A, B, C, or D, it's unstable. The interesting case is when I have one or more roots that are zero. And then it matters, are they case A roots, B roots, C roots, or D roots? If they're case A roots, that's okay. They're still stable because the exponential times a constant, the exponential is a constant, so I just get a constant times a constant. If it's a case B root, it's unstable because I have the exponential is a constant, but it's multiplied by the power of t, unstable. If it's a case C root that has a zero real part, well, the imaginary part, if the imaginary part is non-zero, then it oscillates, but it doesn't grow. So it's still stable, but it oscillates. Case D, if it's a case D root, if alpha L is zero, well, it oscillates, but it also grows to the power of t. So it depends whether it's a case A roots and case C roots, a zero real part are still stable. Case B and D, zero real parts give me things that are unstable. Questions? Well, one thing we should notice here is that when I have linear problems, isn't it kind of cool that I can write CA2 prime in terms of CA in prime? CA2 prime tilde instead of CA2 prime, CA in prime tilde, or CA2 prime in terms of CA in prime when I invert it, that I can write it with no CA1. That is, I eliminated the intermediate variable. So even if I had, let's say, 10 CSDRs in series, I could write CA10 in terms of CA in prime. And I can eliminate CA1, 2, 3, 4, 5, 6, 7, 8, 9. I can only do that because when the problem is linear. But that's kind of a nice thing, that I can do it when the problem is linear. So I have these intermediates, and the nice thing is I can write the output. So for linear problems, I can write the output in terms of the input. And I can eliminate the intermediate variables. Now I might have multiple inputs and multiple outputs. So for example, if I have a CSDR, I can have multiple inputs. I can change the flow rate, and I can change the concentration of the inlet. But here, in this case, I have only a single output. So I might have multiple outputs, or output in terms of various inputs. An I here. And since I can eliminate intermediates for linear problems, I can define something that is the output prime tilde over the input prime tilde. So the Laplace transform of the output in terms of an input. And if I have multiple inputs or multiple outputs, I can have the ith output in terms of the jth input. And I want to do this with primes because I want the initial condition to be 0. Why do I want the initial condition to be 0? Because if you remember the Laplace transform of the derivative, the Laplace transform, recall, is s f tilde of s minus f of 0. So if I arrange for the initial conditions to be 0, I don't have to worry about this f of 0. And this thing is called, we're going to give this a name, we're going to call it the transfer function. And it tells us the output Laplace transform in terms of the input Laplace transform. And we usually call this G tilde of S. I don't know why they call it G tilde of S. Probably the person who defined it, their last name probably started with a G. Just a wild guess. But we call it G, and it's called the transfer function, and it relates the Laplace transform of the output to the Laplace transform of the input. Don't confuse that with Kp. If you remember, Kp, the steady state gain, Kp was defined as the output as t goes to infinity over the input, steady state. The Kp are the steady state values in the time domain. Even though it's a ratio of output over input, it's in the time domain. G tilde of S is not in steady state, and it's in the S domain. And we'll be looking at lots of examples of that. We'll be dealing with transfer functions a lot this semester. So, for example, let's look at a single CSTR. One CSTR. If I have one CSTR, if you remember, I had CA prime over CA in prime. Well, CA prime over CA prime tilde over CA in prime tilde, that's just Kp over 1 plus St. That's just G of S. Notice, in this case, I only had one input and one output, so I didn't have to tell you which one. If I have multiple ones, I will need an ij here to tell you which input, which output. How about two CSTRs in series? Then G of S is CA2 prime tilde over CA in prime tilde. And that's equal to Kp2 over 1 plus St1, 1 plus St2. This guy divided by that guy, which is Kp2 over that. So notice, G tilde actually has the Kp in it. Kp's happen to be inside this G tilde, but they're not the whole thing, the same thing. Question? Okay, well, let's do an example in some detail where I have multiple input outputs. And let's look at a CSTR. CA in and V, CA, where I'm going to be given that at t, that CA in changes at t equals 0. And so does V changes at t equals 0. So how do I handle that? Let's look at that. So let's go through the details. dCA dt, let's write out the CSTR equation. That's equal to little v over big V, CA in minus CA, minus KCA. So I also have the first order range, KCA, with the rate constant K. So we've seen this before. Here I have my CSTR equation. And let's use different colored chalk to see what's changing. Where did my blue chalk go? There was a little piece that ran away. There it is. So what are we changing? I'm going to make those blue. What are we changing? Someone read. What are we changing? V. So we're changing V. And what else are we changing? CAN. As a result of us changing V and CAN, what's going to change as a result of that? What's going to change as a result of that? Someone over here? CA, yes. So all these things are changing. Gee, life is unstable here. The only thing that's staying the same is the volume of the reactor. All right, well, let's go through and do it. So this is the exact equation. Now I need to linearize. The same thing we always do, linearize. So I have dCA dt. It's linear, it's equal to. All right, well, here I have a product of one thing that's changing and another thing that's changing. And we know that A plus delta A times B plus delta B is equal to AB plus B delta A plus A delta B plus delta A delta B. So A has changed a little bit, B has changed a little bit. This is a nonlinear term. Another way of saying that is if I take ddt of AB, I get A ddt plus B dA. So the linear part is A delta B plus B delta A. A delta B plus B delta A. And remember, Taylor says that f of t is equal to f of x is f of x0 plus df dx and x0 times x minus x plus dot. So I get the derivative is this term, so it's equivalent to those two terms. So let's plug it in, and with all that review there. So this thing is A, this thing is B. So here I have V prime over V, CA in of t less than 0 minus CA of t less than 0. So here I'm letting V change, but I'm looking at the steady state value of this guy. Now I look at the change in this times the steady state value of that guy. So I've got V t less than 0 over V, CA in prime minus CA prime. So I've just done this term. Now I need this term. So I need V at t less than 0 over V, CA in at t less than 0 minus CA at t less than 0. So all three of these terms come from here. And now I have minus K CA at t less than 0 minus K CA prime times, minus K CA prime. The derivative of this thing is K minus K times CA prime. Hopefully this is review. Hopefully this is something that you know. And now let's look at the t less than 0 part. dCA at t less than 0 dt is equal to, well, it's equal to V at t less than 0 over V times CA in at t less than 0 minus CA at t less than 0 minus K CA at t less than 0. This is exact. It's this equation, just at t less than 0. And now what I do is I subtract. And when I subtract, I'm going to go up here. So if I subtract, I have dCA prime dt. Is equal to, well, this term cancels this term cancels that term. And I'm left with V prime over V, CA in t less than 0 minus CA t less than 0 plus V t less than 0 over big V, CA in prime minus CA prime minus K CA prime. So all I did, I subtracted. This term survived, these two terms survived. And now what I'm going to do is the usual. Anytime I see a CA prime, I want to bring it to the other side of the equation. So I have a dCA prime dt plus K plus 1 over tau 0. That's 1 plus K tau 0 over tau 0, CA prime. And that's equal to whatever's left on the right. So I've got V prime over V, CA in, that's right, CA in t less than 0 minus CA t less than 0 over V. Plus CA in prime times 1 over tau 0. Where tau 0 is equal to V for t less than 0. It's just the tau before the step change. And I want you to notice something. Let's Laplace transform. So if I Laplace transform, I have CA prime tilde is equal to, this thing is just 1 over t. This is 1 over t plus s, which I can rewrite as CA prime tilde times 1 plus st over t is equal to V prime tilde times this square bracket plus CA in prime tilde over tau 0. I know I'm writing a lot here, but this should all be review stuff. And let's write the next equation. CA prime tilde is equal to V prime tilde times that square bracket times t over 1 plus st plus CA in prime tilde times t over tau 0, 1 plus st. And let's look at this equation right now. So I've just derived this equation. This is CA prime tilde. And notice on the right side, I've got the driving forces. I've got V prime tilde, and I've got CA in prime tilde. These are the driving forces. This 1 plus st over t, t over 1 plus st, came from the system. That was multiplying on the left. That came from the system, not from the driving forces. So, and notice that this is in the form of n tilde over d tilde. I've got d tilde is 1 plus st, both. And the rest may come, if v prime is a step, that will give me a 1 over s. If c in prime is a step, that will give me a 1 over s. But what I can do now is I can come up with the g's before I run out of space. So I can have g tilde in terms of how v prime affects CA. How v prime affects CA. That's just equal to the square bracket. The square bracket, what is this thing? CA in t less than 0 minus CA less than 0 divided by V times t over 1 plus st. So here I have g tilde of s for how V prime affects CA prime. And I have g tilde for CA in prime of s. How CA in prime affects CA as just t over tau 0, 1 plus st. So I'm able to come up with the transfer function for how V prime affects CA prime and for how CA in prime affects CA. Notice I didn't have to do them separately, I did them at once. I just did the algebra once and for all instead of doing it twice. I know I went through that reasonably quickly, maybe unreasonably quickly, but it was all algebra, the kind of algebra you've seen before. So you can just look at this and you should be able to follow it. Let's just review what we did here. What I wanted to do, I introduced the notion of a transfer function. And the transfer function says for each input, how does it affect each output? And I could have multiple inputs and multiple outputs. Here, I looked at a case with 2 input changes, but only 1 output. So I wanted to calculate the transfer function for how each of these guys affects CA out. I wrote out the equations. I went through the standard procedure. Standard procedure is you write the exact equation. You then linearize the exact equation when it's nonlinear. Here it is nonlinear because I've got product of colored variables. I've linearized it. I subtract the exact equation t less than 0. Lots of stuff cancels. And what's left, I bring all the CA primes to one side of the equation. That's the system. And when I Laplace transform, what's left on the right side are the driving forces. So I've got the driving forces on the right. And I notice that once I have it in this form, I immediately know the transfer functions. The transfer functions for how V prime affects CA prime is just this thing. And the transfer function for how CA in prime affects CA is just this thing. Because it's just the ratio of output prime tilde over input prime tilde. Output prime tilde over input prime tilde. Output prime tilde over input prime tilde. Which I just rewrote over here, small enough so that no one can read it until you get the picture. But you know, even if you don't read it, you from where you sit now, it's just this thing. The ratio of this to this is this guy, and the ratio of this to this is this guy. Are there any questions on that, on anything we've done today?